Okay, let us start. In the so all who have joined, please give your attendance in the chat box. Okay, like this. Please all give your attendance in the chat box. Okay, so 25 people have joined. Please give your attendance here. Okay, let us start. So we have discussed up to ultimate bearing capacity, right? So for ultimate bearing capacity, what we have said, if you remember, that if the load is gradually increased on a footing, then there will be an instance coming when the maximum load the footing will be able to take, and beyond that, beyond any little amount of increase of that load, what will happen? There will be shear failure in the supporting soil, and such gross load, such maximum gross intensity of loading will be the soil can support just before it fails in shear is basically called as ultimate bearing capacity. You must very clearly understand this term. This is the primary thing for any foundation engineering. Bearing capacity term and the terms we are discussed in the previous class, and few more terms whatever we will be discussing today, they are very important from foundation perspective. So you see that ultimate bearing capacity, what we have said, it will not only depend on the properties of the soil. That means, see, the particularly it is telling that when the soil will fail in shear, but no, it will not only depend on the properties of the soil. That means it will not only depend on the shear strength properties of the soil, which are nothing but your cohesion and angle of internal friction, but also it will depend on several other things. And what are those several other things? They may be the shape of the footing, the size of the footing, the depth at which you are placing the footing, the mode of loading, that means whether the load is acting vertically on the footing, or the load is acting at an inclined level on the footing, or the load is acting eccentrically on the footing, whether the footing is under some water table or it is not under the water table. Depending on all these factors, the bearing capacity calculation or the value of ultimate bearing capacity is going to change. Now, if we go little forward, then from this, depending on this ultimate bearing capacity value, there are some more definitions, you need to understand, and those definitions are very important. You must remember these terminologies. See, these terminologies looks to very similar to each other. However, you need to remember it separately and you need to remember it properly, because they are type of similar, but they have difference. So let us say ultimate bearing capacity. After ultimate bearing capacity, we are going to understand another one term, that is net ultimate bearing capacity. See, previously we have understood ultimate bearing capacity. Now, what is net ultimate bearing capacity? Now, net ultimate bearing capacity is nothing but if you subtract the overburden pressure of the soil if you subtract the overburden pressure, now what is the overburden pressure? So, the depth of the footing if it is dF and the unit weight of soil if it is gamma, in that case the overburden pressure which is acting on the footing, that is going to be gamma into dF. So, if you subtract the overburden pressure from the ultimate bearing capacity, because if you see, if you go back again to the ultimate bearing capacity equation, then what is ultimate bearing capacity? Actually ultimate bearing capacity, if you see ultimate bearing capacity is saying gross intensity of loading, gross intensity of loading. And what is gross intensity of loading? Gross intensity of loading is nothing but your Q structure, Q superstructure plus Q foundation plus Q soil. So, Q soil is included in it. So, from the gross loading intensity you have got net loading intensity by subtracting what? By subtracting the soil overburden pressure. Exactly the similar way, when you are calculating the maximum gross loading intensity, which is nothing but your ultimate bearing capacity, from that if you want to find out what is the net ultimate bearing capacity, if you want to find out the net ultimate bearing capacity, in that case also what you will have to do, from the ultimate bearing capacity you will have to subtract the value of the overburden pressure. So, definition wise it is nothing but it is the maximum net intensity of loading, it is the net intensity of loading which the soil can support at the base of the foundation before failing in shear. So, see, this is important, maximum net intensity. And what is net intensity? Net intensity means you just subtracting the overburden pressure from the ultimate bearing capacity of soil. Very simple. Mathematically if you think it is very simple, but terminologically if you want to define, you need to remember these terms very carefully, that it is the maximum net intensity of loading which the soil can support at the base of the foundation before failing in shear. Okay. Now, you see, once you have defined the term ultimate bearing capacity, so ultimate means what? Ultimate means you cannot go beyond that, and net ultimate, when you are calculating net ultimate means you are just subtracting the overburden pressure. So, you see the net ultimate bearing capacity, is basically we are obtaining by just subtracting the overburden pressure from the ultimate bearing capacity. So, you see net ultimate bearing capacity value will be always going to lesser than the ultimate bearing capacity value. And how much, by how much amount it will be reduced? It will be reduced by the weight of the soil or the overburden pressure of the soil. Now, if you subtract that amount, so obviously you see the carrying capacity, the carrying capacity of foundation, whatever you will be designing for, ideally you can design it with ultimate bearing capacity, but no, we are not going to design it considering the ultimate bearing capacity. Instead, we will be calculating the net ultimate bearing capacity, and after we are getting the net ultimate bearing capacity, we will be applying some amount of factor of safety F. That means we will be reducing the carrying capacity by some amount, so that our structure or our foundation will be always safe under the load. So, what is net safe bearing capacity? So, see the terminological change, you see previous one was net ultimate bearing capacity, now the next term is net safe bearing capacity. So, you see mathematically it is simple. So, mathematically you see the net safe bearing capacity which is written as QNS. So, QNS is nothing but the previous term whatever you have got, that is QNU divided by F, and F is nothing but the factor of safety. So, it is the maximum maximum net intensity of loading that the soil can safely support without the risk of shear failure. Without the risk of shear failure. It is obtained, how it is obtained? It is obtained by dividing the net ultimate bearing capacity. See, this is your NU is nothing but your net ultimate bearing capacity. If you divide this net ultimate bearing capacity by a factor of safety, you are going to get the net safe bearing capacity of the foundation. Okay. Now, going forward, you see another one term we need to understand, that is gross safe bearing capacity. Now, what is gross safe bearing capacity? So, you see gross safe bearing capacity is again a term which is coming from the net safe bearing capacity. You see, every term is related, mathematically. If you see, every term is related. First you are getting QU. QU means ultimate bearing capacity. From QU, that is the ultimate bearing capacity, if you are subtracting the value of the overburden pressure, you are getting QNU. What is QNU? It is nothing but net ultimate bearing capacity. Now, once you get the net ultimate bearing capacity, if you divide the net ultimate bearing capacity by some factor of safety, you are going to get the maximum net intensity of load that the soil can safely support without the risk of any shear failure, and that value will be termed as net safe bearing capacity. So, you are going to get QNS in that way is equal to QNU by F. Now, once you get the QNS, now if you add up again the value of this gamma dF, because you see this gamma dF is going to exist on the soil. Gamma dF is going to exist. You cannot just subtract gamma dF from the thing. So, once you have got the safe loading on the foundation, because what you are doing by this way, you see, you are subtracting the overburden pressure, adding the effect of factor of safety onto it, and then again you are going back and adding up the value of the overburden pressure. So, you see, in this way, through these three terms, what we are actually trying to do, we are actually trying to remove the effect of factor of safety for the overburden pressure, because you see here we have not applied any factor of safety, and after subtracting the overburden pressure, we are applying factor of safety, and again we are going back, again we are going forward, and then adding up the overburden pressure without any factor of safety, because for the soil overburden pressure we cannot take any kind of factor of safety as such. So, the maximum gross intensity of loading that the soil can support safely without the risk of shear failure, that will be called as gross safe bearing capacity. Very important these terms are, don't get confused. So, serially you should remember this term: net ultimate bearing capacity, then net ultimate bearing capacity, then net safe bearing capacity, then gross safe bearing capacity. Now, coming to the another term, that is safe bearing pressure, very important term. See, safe bearing pressure, this is little different than your those bearing capacity things. See, here the term is not, it is not in the previous term. You see, you have seen safe bearing capacity. Here you see the term is safe bearing pressure. So, what is the difference, bearing capacity and bearing pressure? See, initially when we have started our discussion, I was emphasizing on 2 points, that soil can fail by shear failure as well as it can fail by settlement failure. So, you see, you need to consider the failure effect by both of them, that is shear failure and settlement failure. So, your foundation should be such that it should not fail in shear failure as well as it should not fail by settlement. So, this safe bearing pressure is a term which will be assigned to that settlement failure. So, basically definition wise, if you see, the safe bearing pressure is nothing but it is the maximum net intensity of loading. Again you see the maximum net intensity of loading, which we have which we have already understood here also. Net safe bearing capacity, you see, in case of net safe bearing capacity also we have said maximum net intensity of loading. Here also we are saying maximum net intensity of loading, but these two terms are different. This is safe bearing capacity, whereas here it is safe bearing pressure. These two terms are totally different, don't get confused. So, maximum net intensity of loading that can be allowed on the soil, very important here, without the settlement exceeding the permissible value. So, you understand now? So, safe bearing capacity is related to the load, or it is related to the shear failure of the soil. So, without the risk of shear failure when you are telling, then it is safe bearing capacity, whereas when you are telling without the settlement exceeding the permissible value because of some maximum net intensity of loading, such kind of intensity of load will be called as safe bearing pressure. For time being, you should remember that safe bearing capacity or net safe bearing capacity and safe bearing pressure are typically two different terms. One is dependent on shear failure and the other one is dependent on shear settlement failure. And here you should understand another one term. See, this net word is not there, you see, net word is not there here. So, only safe bearing pressure we are saying, and in this case for this settlement failure of soil, you must remember no factor of safety can be used. So, in case of settlement failure, when you are considering, no factor of safety is used while dealing with the settlement. So, this value, this safe bearing pressure, actually you will be getting from the settlement analysis of soil, basically the consolidation settlement, immediate settlement you have learnt in your 4th semester course. From those terms, again there are some codal provisions, Indian standard codes are there. From those standard codes you should be able to find out this safe bearing pressure. Okay. Now you see, then for what value we will be designing our foundation. So, you see, our foundation should not fail because of shear as well as our foundation should not fail because of settlement. So, basically you see, allowable bearing pressure, the final term whatever you are seeing here, allowable bearing pressure, this allowable bearing pressure is nothing but it is the maximum net intensity of loading. It is the maximum net intensity of loading that can be allowed on the soil with no possibility of shear failure or the possibility of excessive settlement. Are you getting? So, allowable bearing pressure is the final thing we need to reach for designing any foundation. So, we will have to consider the shear failure criteria, we will have to consider the settlement failure criteria, and depending on that, the maximum load intensity which the foundation can bear, or which the maximum load intensity which can be allowed on the soil, or the value of maximum load intensity which is being transferred from the foundation, transferred through the foundation to the soil without having any chance of either shear failure or without the chance of settlement failure. So, that much maximum net intensity will be called as allowable bearing pressure. and you see it is the minimum. Basically that means what? That means you see the net safe bearing capacity, whatever you have got, this net safe bearing capacity, as I have told you, this net safe bearing capacity and safe bearing pressure, they are similar terms, but you see in case of net safe bearing capacity you have applied the factor of safety. In case of safe bearing pressure you have not applied factor of safety. In case of net safe bearing capacity you are considering, you are just minimizing or removing the risk of shear failure. In case of safe bearing pressure, what you are doing? You are removing the risk of settlement failure or exceeding the permissible settlement. So out of these two terms, out of this, see both the thing is saying net intensity of loading. So one net intensity of loading you will be getting from net safe bearing capacity, another net intensity of loading you will be getting from safe bearing pressure. Out of these two, whatever will be minimum, because of that your foundation soil will fail. So allowable bearing pressure is nothing but the minimum of the net safe bearing capacity, minimum of this net safe bearing capacity, which is basically dependent on the shear failure criteria, and the safe bearing pressure. Safe bearing pressure means this one, which is basically driving the settlement criteria. Is it clear to everyone? Do you have any doubt on this? Is it clear? Hello? Any question up to this definition? Do you have any question up to these definitions? Very important these definitions are, okay. So see 7-8 definitions we have understood till this. All these definitions are very important. All these definitions are very important, okay. So you must very carefully read these definitions. You can read it from this slide, you can read it from any book, okay, but you should be very careful about these definitions, and these definitions need to be read basically basically serially. You need to remember this, otherwise you may get confused. So first you should understand gross pressure intensity, then net pressure, then ultimate bearing capacity. From ultimate bearing capacity you are going to get net ultimate bearing capacity. From net ultimate bearing capacity you are going to get net safe bearing capacity. From net safe bearing capacity you are going to get gross safe bearing capacity, and then suddenly you see there is another one term coming, that is safe bearing pressure, which is not related to the shear failure criteria, that is settlement failure criteria, which we will be separately understanding in another chapter when we will be understanding the settlement analysis of soil. But here you need to understand the safe bearing pressure, because you see soil may fail under the load because of the shear failure or settlement failure under any foundation. So allowable bearing pressure, whenever you will be calculating this, allowable bearing pressure will be the minimum of net safe bearing capacity and safe bearing pressure, okay. Let's chalo next, let us now try to understand. So you see, you have seen that this one ultimate bearing capacity, right? So if you know this, see for shear failure criteria, for any shear failure criteria, see for any shear failure criteria, if you want to find out the failure of the soil or the failure of the soil under the foundation, then you must be able to calculate the ultimate bearing capacity. So there must be some methodology to find out this ultimate bearing capacity. And how do you find out this ultimate bearing capacity? This finding out of ultimate bearing capacity is primarily given, and initially it has been given by Terzaghi, okay. Terzaghi's name you have already heard in soil mechanics, right? So again in foundation engineering, again you see Terzaghi's name again will come, and Terzaghi has given the theory for this finding out the bearing capacity. And which bearing capacity he has told about? He has told about the ultimate bearing capacity. So, in 1943, see the year when the Terzaghi has discovered the general shear failure criteria and local shear failure criteria. You remember the general shear failure and local shear failure and punching shear failure we have discussed. So, you see Terzaghi has discovered in 1943 he has discovered the general shear failure and local shear failure criteria, whereas in 1963 Vesic has found out there is another one shear failure criteria, which is punching shear failure. And while working on these things, Terzaghi has come up with the bearing capacity theory, and this bearing capacity theory, you see, it has been presented on in the year 1943, and it gives a comprehensive theory. It's a comprehensive theory, very important theory. He is the father of soil mechanics, you can say, because this Terzaghi is, without Terzaghi's bearing capacity theory, you cannot calculate bearing capacity as such. Basically, he has given the concept of bearing capacity first and how to calculate it. So, the comprehensive theory for the evaluation of the ultimate bearing capacity. So, you see what is being given by Terzaghi. Terzaghi has given the theory to find out for finding out the ultimate bearing capacity. Okay? So, Terzaghi has given the theory for finding out ultimate bearing capacity, right? So, this ultimate bearing capacity, and second point you should see, he has given the theory for shallow foundation and the rough shallow foundation. That means the below the foundation there is some roughness, it is not at all smooth, completely smooth foundation, it is not smooth. The surface at the bottom of the foundation is not smooth, it is a rough shallow foundation, and you understand now what is a shallow foundation. So, you see the Terzaghi's theory, whatever he has presented for finding out the evaluation of bearing capacity is valid for rough shallow foundation, and it is giving only the ultimate bearing capacity. It is only giving the ultimate bearing capacity. So, according to this theory, according to his theory, what he has said, that foundation is shallow. A foundation is shallow, you know it already, we have discussed it earlier also. A foundation will be considered to be a shallow foundation if the depth of the foundation, that df, that is the depth of the foundation, is less than or equal to the width of the foundation. You must understand this very clearly. Always it will depend on the width of the foundation, not the length of the foundation. Always will be considering the shorter dimension of the foundation. So, when the depth of the foundation is less than or equal to the width of the foundation, we will be considering them as shallow foundation, and according to Terzaghi's bearing capacity theory, the bearing capacity calculation, or the ultimate bearing capacity formula or ultimate bearing capacity theory will be valid for only such foundation. Now, while doing the bringing this bearing capacity theory, or while deriving this bearing capacity theory, Terzaghi has assumed few of the things. So, these few assumptions are very important, because without these assumptions you cannot have the bearing capacity equation in the form of Terzaghi. Now, what are the basic assumptions Terzaghi has taken while doing this bearing capacity analysis or bearing capacity theory? What is bearing capacity theory? See, the first assumption Terzaghi has taken is very important, that is, soil is semi-infinite, it is homogeneous, and it is isotropic. Now, these three terms in soil mechanics or in foundation engineering are very important. See, all these three terms, most of the soil mechanics theory or foundation engineering theory, bearing capacity theory, whatever you say, they will assume these three things, that soil is semi-infinite, soil is homogeneous, and soil is isotropic. So you should understand what are these three things properly. So semi-infinite means, you see, it can extend in the infinite direction in one direction. It can extend in infinite direction in only in one direction. It cannot extend in the other direction, because you see, on the if you are analyzing a soil, you see on the earth surface, its extension beyond the earth surface, it is not extending, right? So it is only extending in the downward direction. So soil is extending in the downward direction to the infinite level, and that is actually semi-infinite. Next is homogeneous. So what is homogeneous? Homogeneous means the properties of the soil. So if you take different positions underneath the ground, if you take at different positions the soil, the properties of the soil assumed to be remaining same. That is actually homogeneity. The property of the soil is remaining same, which is not exactly the case always. You see, soil will not be exactly same, but there is an assumption. If you cannot take such assumption, you cannot derive the theory of bearing capacity. So this assumption is being put into consideration, that soil is homogeneous. That means the material properties are same. So here some portion of soil you take somewhere, and then you go a little bit other distance, and then you take it. So there also the soil property will be remaining same. So if you collect a sample from one place around some area, you are assuming that the property of that sample will be remaining same throughout that area. So that is actually homogeneity. Okay, and the last one is isotropic. And isotropic, you must be knowing that you are from your strength of material course, you know what is an isotropic material. Isotropic material means the elastic property of the material will remain same in all directions. So elastic property, if there is a three-dimensional material, and most of the material or most of the things are in three-dimensional nature, if the material property in all the directions remains same, that means if the elastic constants in all directions remain same, that means modulus of elasticity, Young's modulus, those things, Poisson's ratio, if they are remaining same in all directions, in such case a material will be called as isotropic material. In the assumption of Terzaghi's bearing capacity theory, this isotropic nature of soil is also considered. So it is being considered that the elastic property of soil is remaining same in all the directions. Now the next important assumption for Terzaghi's bearing capacity is very important assumption. See, the L by B ratio. So what is L? L is the length of the footing and B is the breadth of the footing. So L is always the larger dimension and B is always the shorter dimension. So what the Terzaghi's formulation, what it assumes, that the L by B ratio, that means length to breadth ratio, is always large. That means value of L by B is always greater than 1, and the problem is two-dimensional. And the plane strain problem, basically this assumption, if you in a simplified way, if you understand, basically this says a plane strain problem means it is basically Terzaghi has derived this bearing capacity equation for a strip footing. If you remember what is a strip footing, we have shown it, right? Strip footing, see, this is your strip footing. If you remember, strip footing. So this is your strip footing, So what is the strip footing? You see, this is your breadth of the foundation, and you see this is your length of the foundation. So if a foundation is like this, you see the L by B ratio will be much greater than the 1, and that kind of foundation will be considered as a strip footing or a continuous footing. So the Terzaghi, the derived formula for Terzaghi is basically considering such kind of footing, that is a strip footing, where because of this L by ratio is large, the problem becomes a two-dimensional problem and it becomes a plane strain problem. Now point number 3, that the third assumption, if you see, third assumption, it's very simple assumption. See, without this assumption the bearing capacity equation does not work at all. That is, already we have discussed it, the depth of the footing is less than or equal to the width of the footing. That is the basic assumption for Terzaghi's bearing capacity, that it is always valid for only the shallow foundation. It is only valid for shallow foundation. So depth of the footing is less than or equal to the width of the footing, that is dF is less or equal to B. Basically this assumption says that bearing capacity theory will be only valid for shallow foundation. Now the fourth assumption, that is also very important. See, in Terzaghi's bearing capacity equation, Terzaghi hasn't considered anything for settlement failure of the soil, and he is only considering the criteria of shear failure of the soil. So Terzaghi's bearing capacity formulation only considers that the soil fails by shear, and you see very important assumption is this one, it fails by general shear failure. You remember what is general shear failure? General shear failure we have discussed, right? So general shear failure is nothing but this one. So Terzaghi's assumption is this one. So see, Terzaghi 1943, whatever he has given, so the theory whatever he is deriving for bearing capacity equation, it is assuming this kind of failure. So there are 3 clearly demarcated zones of failure with bulging of soils, with common failure mode in foundation and in dense kind of soil where the relative density is greater than 70%. So Terzaghi's bearing capacity equation considers the soil is essentially failing by shear. And which kind of shear? Failure? The failure is general shear failure. Very important assumption. Then the next assumption is shear strength of soil is governed. It is governed by Mohr-Coulomb's failure criteria. You remember Mohr-Coulomb failure criteria? I have explained it. What is Mohr-Coulomb failure criteria? Mohr-Coulomb failure criteria is nothing but that straight line equation is where tau, the shear strength of soil or the shear stress in soil, tau is given by tau is equal to C plus sigma tan phi, where C is nothing but your cohesion and sigma is the overburden pressure in the soil and phi is the angle of internal friction. And if you plot sigma along the x axis, that is the overburden pressure along the x axis, and tau, the shear stress in soil, along the y axis, then you are going to get a straight line which will have an intercept on the y axis with a value of C, and which will be making an angle of phi, that is the angle of internal friction, with the horizontal x axis. And that straight line equation will be given as tau is equal to C plus sigma tan phi, and that is actually your shear strength of soils governed by Mohr-Coulomb failure criteria. Okay. Now last two assumptions you will be seeing it while deriving some equation. It's not very important that you need to understand the derivation of the equation, but you should understand the assumption of the bearing capacity properly. That's what I have given the 6th and 7th assumptions also. See, 6th and 7th assumptions are the shear resistance of soil for the depth df is neglected. What does it mean? It means that it is assumed by Terzaghi in his bearing capacity equation that the soil below the footing only will be participating in the resistance, shear resistance, only it will be giving shear resistance. The shear resistance will be only given by the soil below the footing. सॉइल का ऊपर, फुटिंग का जो ऊपर का सॉइल है, ग्राउंड लेवल से फुटिंग तक डेप्थ का जो सॉइल है, द अमाउंट ऑफ सॉइल विच इज रेस्टिंग above the footing, above the base of the footing, Terzaghi assumed that that portion of the soil will not be giving any kind of shear resistance. Only the shear resistance will be given by the soil below the footing. And finally, the last assumption by Terzaghi is the overburden pressure at foundation level, is equivalent to the surcharge load. This is nothing but your assumption of total load which is coming because of the soil weight is nothing but your overburden pressure. So these 7 assumptions are very important. You should remember these 7 assumptions. Okay, 7 assumptions. So with these 7 assumptions, Terzaghi has derived his bearing capacity equation. Okay. So now let us go to Terzaghi's bearing capacity equation, what it says actually, and what is Terzaghi's assumption, what is Terzaghi's theory, actually bearing capacity theory. Sorry.
सर सरचार्ज लोड क्या होता है सर? 7th पॉइंट में दिया हूँ.
Pardon, एक मिनट. सरचार्ज
लोड.
हाँ,
Yes,
surcharge load. See, overburden pressure at foundation level. At the foundation level, if you want to find out what is the load acting, okay, that will be calculated using the unit weight of the soil multiplied by the depth of the foundation, and basically that is actually your surcharge load. See, surcharge load, if you want to understand properly, you should go back again to the soil mechanics. Okay, soil mechanics में अगर आप देखेंगे एक जगह में आप लोगों इफेक्टिव प्रेशर कैलकुलेशन का एक चैप्टर पढ़ा हुआ है, इफेक्टिव प्रेशर, हाउ टू कैलकुलेट इफेक्टिव प्रेशर. So in that chapter you will notice that in some cases on the top of the footing, on the top of the ground level, some UDL kind of load was given. So this UDL kind of load is basically the surcharge load. Okay.
Okay sir.
Okay. So basically you consider this is nothing but the overburden pressure. So overburden pressure, please mute, whosoever is unmuted, please mute. Okay, some background noise are coming. So you see this overburden pressure, how do you calculate overburden pressure? It is very simple. It is nothing but, see, unit weight of soil. What is the unit weight of soil? Unit weight of soil means kilonewton per meter cube. Right. So kilonewton per meter cube multiplied by meter, that is the depth of the foundation if you do. So you are going to get a stress unit, that is kilonewton per meter square. So that is actually your overburden pressure. So that gamma df term we are talking about, gamma df. So that gamma df term is actually your overburden pressure. Now let us go to this one. So see, this shallow foundation, Terzaghi's bearing capacity theory, you see what Terzaghi has said. So Terzaghi, see, suppose you have a foundation this one. So suppose you have a foundation this way, and what kind of foundation Terzaghi has said, this should be a strip footing, and we are only concerned about this B. We are not concerned about how much length this foundation having in this direction, because the formulation is given considering it is a two-dimensional problem. It is not considering it is a three-dimensional problem. So only two dimensions of the foundations will be concerned about while deriving the Terzaghi's bearing capacity theory, that is breadth of the foundation and depth of the foundation. So you see, this breadth of the footing, let us say it is B, and the footing is a strip footing. So on the other direction, on this third dimension, the footing may have a length L, which is much more than this breadth B. Now this footing, you see, it is placed at a depth D. Can you notice this placed at a depth D? Now you see, for this portion the soil will not participate in shear resistance. That is what is Terzaghi's assumption. You see what it is said, shear resistance of soil for the depth df is neglected. So this is what is being done here. The shear resistance of the soil for this portion is being neglected, and that is why you see, while discussing about general shear failure, whatever diagram we have shown, you see that portion of the diagram is shown below this depth D, below this depth df, because the shear resistance from the ground surface to the depth of the footing will be neglected. That is what is Terzaghi's assumption. And after that, you see, after that surcharge weight, that just few minutes back you have asked a question also, that what is surcharge load. You see, surcharge load is nothing but a load will be coming and acting at this level on the soil, you see, along with this foundation load. The load from the soil will be also coming, because you see, this portion of the soil, and this portion of the soil will be creating some pressure on the at this level, right. So this level or the pressure from the soil, whatever will be coming and acting at the depth level of the footing, that will be considered as surcharge load. And how will you get it? So basically you see this arrow marks. So these arrow marks are nothing but kind of UDL kind of thing, right. And see, that is actually your effective overburden, and this is your actually this is your surcharge weight. So this effective overburden Q is equal to gamma df, if you notice here. So that is actually your surcharge weight or overburden pressure. I hope this is clear now. Okay. Now you see, this below this foundation, what Terzaghi has assumed, that soil is necessarily failing by general shear failure. So when the soil is failing by general shear failure, if you remember general shear failure criteria, then you see general shear failure criteria, what is happening, that soil will be failing in three zones, three clearly demarcated zones. I have explained it, right. So you see, the first zone will be a triangle shaped wedge zone, and this zone will be termed as zone 1, and this zone will be called as zone of elastic equilibrium. Okay. So zone of elastic equilibrium. So what is the zone of elastic equilibrium? See, zone of elastic equilibrium is the zone just underneath the footing, which will be just in a triangular wedge shape and will be getting attached to the footing. So when the load will be coming from the footing, it will be just trying to compress it down. So along with this footing, a triangular wedge zone will be trying to pushing inside the soil, and because of pushing inside the soil will be getting compressed into other zones, right, other portions. So along when this soil is trying to get pushed using the foundation load, along with this soil load of this triangular wedge shaped zone, which is nothing but your zone of elastic equilibrium, which is nothing but zone of elastic equilibrium, you are going to get another one zone just beside it, and that is called zone 2, and this zone 2 is called zone of radial shear failure. You see, while the footing is trying to get inside the soil by the pressure, at that time there will be some kind of radial pressures will be coming in this zone. Radial pressures will be coming in this zone in the radial direction. So radial pressures will be coming in this zone, this way, this way, this way, this way, this way. So this radial pressures, the zone which is, you see, it is a kind of spiral shaped zone. You see, some kind of spiral it is forming. So in this spiral shaped zone, the spiral shaped zone, just by the two side of this zone 1 or zone of elastic equilibrium will be called as zone of radial shear failure. And just beside this zone 2 there will be another two properly demarcated zones, and these zone will be called as zone of Rankine passive state. Has Sainton sir discussed about Rankine's active earth pressure and passive earth pressure?
No, sir.
Not yet. Okay. So when Sainton sir will discuss, then you will be able to understand what is passive earth pressure. So basically, you see, when I just simplified way I will tell you what is happening. When this zone is trying to pressurize this, there will be some kind of radial pressure coming in this zone, and these two zones again will be trying to go away in this two direction, whereas because of this surcharge weight from here and here, this zone 3 will be trying to keep this zone into its proper place. So there will be a pressure coming from this direction and pressure coming from this direction, and that's what is basically a passive kind of state, which has been discovered by Rankine. Okay, so when Sainton sir will discuss about active pressure and passive earth pressure, you will be able to understand it more clearly. Now you see, you should remember in this Terzaghi's bearing capacity theory thus that the soil will be necessarily failing by general shear failure, and because of the general shear failure, what you are actually getting, you see, you are actually getting three clearly demarcated zones, that is zone 1, zone 2 and zone 3. So zone 1 is the zone of elastic equilibrium, zone 2 is the zone of radial shear, and zone 3 is the zone of Rankine passive earth pressure. And you see, here you should see very carefully, see, according to this theory, if the angle of internal friction of soil is phi, in that case you see, this wedge, whatever will be attached below the base of the footing, that is the zone 1, that is the zone of elastic equilibrium, you see, that is making an angle of phi with the horizontal, that is the base of the footing. That means you are going to get an equilateral triangle, isosceles triangle. Okay, so you are going to get this side and this side exactly equal because the angle which is going to be made by this zone of elastic equilibrium, this triangle shaped zone, will be exactly equal to the angle of internal resistance. And you see, the zone of radial shear, the zone of Rankine passive pressure, the zone of Rankine's passive state, this shear plane, you see, up to this it is a spiral, and beyond this, you see, this is a straight line. Up to F it is a spiral, and beyond this, you see, it is a straight line. So you see, these straight lines are going to make an angle of how much? 45 degree minus phi by 2. This side also it should make an angle 45 degree minus phi by 2. This thing already you have learnt, I think, from your shear strength of soil, that if you remember, there was a formula something like tan square phi by 2, something like that, tan square 45 degree plus 5 by 2, what is this equal to, C is equal to, some formula is there, I forgot that one. So, from that only it actually comes that this shear plane will be, sorry, not the shear plane, this zone of Rankine passive pressure, this straight line whatever it is making, that will be making an angle of 45 degree minus 5 by 2 with the horizontal. Horizontal means the horizontal line which will be going through the base of the footing. So, this is actually Terzaghi's.
So in this section इसमें जो फाउंडेशन के नीचे जो प्लेन बन रहा है, इन शॉर्ट मतलब एंगल ऑफ फेलियर प्लेन जो बन रहा है, मतलब एंगल वो अल्फा का डिग्री तो जनरली हम लोग इफेक्टिव स्ट्रेस में पढ़े थे, जब प्रिंसिपल स्ट्रेसेस वगैरह पढ़े थे उसमें था 45 प्लस 5/2, तो यहाँ पे 45 माइनस 5/2 है, कोई डिफरेंस है?
Here it will be 45 degree minus 5 by 2, that was 45 degree plus 5 by 2. Here the angle it will be making, because of this Rankine passive state, it will be 45 degree minus 5 by 2. When you will be learning about your what is called active earth pressure and passive earth pressure, you will be more clear on this. Okay, Sayantan sir will teach you this thing. Okay, Sayantan sir will teach you about active earth pressure and passive earth pressure. Okay, but for time being, you remember that this zone of Rankine passive state will be making an angle 45 degree minus 5 by 2 with the horizontal. Okay. So, you see, this is basically general shear failure criteria. This is actually general shear failure criteria. And using this general shear failure criteria, Terzaghi has derived some equation which is very simple to understand, actually looks to be very complex in derivation, but actually it is very simple to understand. He has done a very simple calculation of equilibrium of this wedge. Whatever the wedge it is being connected, whatever the wedge is connected to the footing, on that wedge whatever forces are acting, he has calculated the equilibrium of those forces, and just equilibrium condition weights he has found out and equated in some equation, and then finally he has derived a equation which is called Terzaghi's bearing capacity equation. I will not suggest as of now to go through this derivation step by step, just you remember that this equation is being derived using only the method of equilibrium equation, elastic equilibrium equation. So, you see this elastic triangle, this triangle will be subjected to some forces, and because of those forces, if you consider the equilibrium of this triangular wedge, then you are going to get finally a equation which will be called as, with some simplification and some other things, which will be finally you will be getting, which will be called as Terzaghi's bearing capacity equation, and which is nothing but this one, that Qu is equal to Cnc plus Qnq plus 0.5 B n gamma. We will discuss it in more detail in the next class, because this is very important equation. Throughout your civil engineering life you should be remembering this equation. Okay, and what are these Nc, what are Nq, what are N gamma, those things we will understand in our next class. Okay. So, I think up to this whatever we have discussed, it is hopefully clear to you. So, in tomorrow's class we will be discussing more about this bearing capacity equation and how to calculate these values of this Nc, Nq, N gamma, and what are the codal provisions, how do you get it from the code, what will happen if the soil is not failing by general shear failure, if it is local shear failure, what will happen if the foundation is not a strip footing, then how do you apply Terzaghi's bearing capacity theory. All those things we will be discussing in the next class. Okay. So, any question if you have, just 1 or 2 minutes. if you have any question. Do you have any question? No question. Utkarsh has joined. Utkarsh, he hasn't joined today. Any question? No question. Hello. Hello. Shubhadeep. Hello.
No, sir.
Okay. 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 See, then we'll stop today here. Tomorrow again we'll discuss further about your this thing, bearing capacity equation. Huh? Okay. So today I'll send one quiz. Please participate. Huh? Okay. So
Okay,
I'm
sir.
stopping here. Okay. Thank you. Thank you very
Okay,
much
sir.
for joining. Okay. Thank you.